Dear students, this is lecture 25 of CS218 Data Structures and Algorithms. Assalamu alaikum. We are going to talk about graphs and we used chapter 8 of book 4 for this topic. In the last lecture, we were introduced to graph terminology. We stored the graph in memory and we computed path metrics for the graph. The shortest path algorithm or SPA. The shortest path algorithm, also called Warshall's algorithm, is used to find the path with the shortest weight between each pair of nodes in a weighted graph. A weighted graph is a graph in which each edge is labeled with a number called its weight. You see a weighted graph over here. Each edge has a number associated with it. The weight may represent any quantity of interest like cost of using this edge or the time delay occurring on this edge or the distance covered in going from one end of this edge to the other, etc. How do we execute the shortest path algorithm? I show you with the help of an example. Here is a weighted diagram and the first part is to find the weight matrix W for this diagram. The weight matrix W is computed thus. I am going to read it. I will read the row heading first and the column heading last. There is an edge from R to R of weight 7. There is an edge from R to S of weight 5. There is no edge from R to T, no edge from R to U. There is an edge from S to R of weight 7. There is an edge from S to U of weight 2, but no edge from S to S and no edge from S to T. There is an edge from T to S of weight 3, no edge from T to R, no edge from T to T, no edge from T to U. There is an edge from U to R with weight 4. There is another from U to T with weight 1. There is no edge from U to S and no edge from U to U. We construct n plus 1 matrices from Q0 to Qn, where n is the number of nodes in the graph. So this means that for this graph, the last matrix that we will construct will be Q4. Q0 is derived from W, replacing all zeros with infinity to depict the absence of an edge between two nodes. This is Q0. I have replaced all zeros with infinity. Why have I done that? The shortest path algorithm favors the shortest value, the smallest value of the weights. So if we keep zeros, it will start favoring the zeros because it will think that this is a path of zero weight. But this is not the case. Zeros means that this is not a path. There is no edge. There is no path. So to preserve that meaning, we replace zeros with a number which is too large and it can depict infinity. So this stops the shortest path algorithm from favoring an edge or a path which is not present. This is the reason for replacing zeros with infinity. The other thing to note here is that Q0 is not one matrix, it is two matrices. One matrix contains the weights and the other matrix contains the path names. Again, each path name starts from the row heading, ends at the column heading. So 7 is RR and 5 is RS in the first row. In the second row, 7 is SR and 2 is SU. In the third row, 3 is TS. In the fourth row, 4 is UR and 1 is UT. Now let us place Q0 in front of us. Fix the first row and the first column to compute Q1. Look at this. I have changed the color of the first row and the first column to show you that these entries are fixed. In Q1, we will keep these entries the way they are, and we will compute the other entries according to these fixed entries. Concentrate on the SS entry. It lies at the intersection of 7 and 5. Whenever you are looking for intersection values, look in the fixed column and in the fixed row. 7 is SR and 5 is RS. Its old value is infinity. Its new value is 7 plus 5, which is 12. We select the smaller of the new and old values for Q1. So this means that we select 12. So the weight has changed. The path will also change. The resulting path is found by concatenating SR and RS, dropping one of the repeating R's. So this gives us SRS. Always remember, this is the SS entry. So it will start with S and it will end with S. And if you are concatenating correctly, there will be one character which will be repeating. Like here, the character that is repeating is R. So we drop one of the instances of the repeating character. The new value is 12. The new path is SRS. See how we bring about the change. I hope that you understood how I did this. Now concentrate on the ST entry. It lies at the intersection of 7 and infinity. Again, for intersection values, I am looking at the fixed row and the fixed column. 7 is SR and infinity simply represents the dash, no path or no edge. Now, the old value of the ST entry is infinity, and if we compute the new value, that will be 7 plus infinity, so it will be still infinity. So this means that we cannot bring about a change here. So we leave this entry unchanged. Whatever it was, we simply copy it from Q0 to Q1. Now concentrate on the SU entry. It lies at the intersection of 7 and infinity. Its old value is 2. Its new value is 7 plus infinity, which is infinity. We select the smaller of the new and old values for Q1. So we select 2. And since this is the older value, the old path is left as it is. In this way, I have completed the row of S. Now I will walk you through the other entries. Consider the TS entry. The old value is 3. This entry is at the intersection of 5 and infinity, so the new value will be infinity. So we leave the old value as it is. Now I come to TT. The old value is infinity and this lies at the intersection of infinity and infinity. So the new value will also be infinity. I let it be. Now I am working with the TU entry. The new value is going to be infinity because it lies at the intersection of infinity and infinity. The old value is also infinity, so I let it be. This completes the row of T. Move to the row of U. Come to the entry US. The old value is infinity. The new value is found by adding the intersection values. The intersection values are 4 and 5. So the new value would be 9. So what will we commit here? We will commit 9 because that is smaller. Now we have to write the path for this entry 9. See that 5 is RS and 4 is UR. How do you concatenate them? Your final entry should begin with U and end at S. Begin with the row heading and at the column heading. So we have UR and RS. And you can see that R is repeating. So we drop one R and the path for 9 becomes URS. Now I move to the UT entry. The previous value is 1. The new value is found by adding 4 plus infinity, which will be infinity. So I let the old value be. Talk about the UU entry. The old value is infinity. It lies at the intersection of 4 and infinity, so the new value will also be infinity. I let it be. This completes the matrix Q1. Keep Q1 in front of you. Now we are starting another iteration of SPA in which we will create Q2. Fix the second row and the second column to compute Q2. This is what I want you to do. I have taken away all the other entries and highlighted the second row and the second column. Now all other entries will be computed with these values. These values will be the intersection values. Concentrate on the RR entry. It lies at the intersection of 5 and 7, RS and SR. Its old value is 7. Its new value is 5 plus 7, which is 12. We select the smaller of the new and old values for Q2. That is, we select 7. The old path is left as it is. So you see that for RR we have 7 and the old path RR. Let us move to the RT entry. The old value is infinity. The intersection values for RT are 5 and infinity, which will give infinity. So we let the old value be. Concentrate on the RU entry. It lies at the intersection of 5 and 2, RS and SU. Its old value is infinity. Its new value is 5 plus 2, which gives us 7. We select the smaller of the new and old values for Q2, that is, we select 7. The resulting path is found by concatenating RS and SU. The final path should begin with the row heading and at the column heading, that is, begin at R and at U. So we concatenate RS with SU, dropping one of the repeating S's, and we get RSU. which we will commit. Concentrate on the TR entry. It lies at the intersection of 3 and 7, TS and SR. Its old value is infinity, its new value is 3 plus 7, which gives us 10. We select the smaller of the new and old values. For Q2, we select 10. The resulting path is found by concatenating TS and SR, dropping one of the repeating S's. We get TSR. So we have just completed selection of the entry for TR. Move to TT. The old value is infinity. The intersection values are 3 and infinity, which will give infinity. Let the old value be. Come to the entry TU. The old value is infinity. The intersection values are 2 and 3, which will give 5. So we commit 5 for TU. Now let us talk about the path. 3 is TS, 2 is SU. TS and SU drop the repeating S. For 5, the resulting path is TSU. Begins with T, ends at U. This completes our row for T. Come to the row for U. Look at the UR entry. The old value is 4. The intersection values are 7 and 9, which will give 16. But 4 is smaller, so we opt for the old value. And the old path remains as it is. Now we have to decide for the UT entry. The old value is 1. The intersection values are 9 and infinity, which will give infinity, so we let the old value be. Come to the UU entry. Here the intersection values are 9 and 2, which will give 11. The old value is infinity, so we select 11 because it is smaller. What about the path? 9 is URS and 2 is SU. Drop the repeating S. The final path is URSU, which we commit for 11. This completes our matrix Q2. Keep Q2 in front of you. Now we will start another iteration in which we will work out Q3. Fix the third row and the third column to compute Q3. This is what we do. Eliminate all the values, just keep the third row and the third column. Now we will look for intersection values in this row and this column. So I have worked out a few values here which I will walk you through one by one. First, the RR entry. The previous value was 7. The intersection values are 10 and infinity, which will give infinity, so we let the previous value be. Now I am focusing on RS. The previous value is 5. Intersection values are 3 and infinity, which will give infinity. So I keep 5. Now come to RU. The previous value is 7. The intersection values are 5 and infinity, which will give infinity. So I opt for 7. This completes my row of R. Come to the row of S. I am focusing on the entry SR. The previous value is 7. Intersection values are 10 and infinity, which will give infinity. So I keep 7. Come to the entry SS. The previous value is 12. Intersection values are 3 and infinity, which will give infinity. So 12 is better and I keep it. Come to the entry SU. The previous value is 2. Intersection values are 5 and infinity, which will give infinity. So I keep 2. Concentrate on the UR entry. It lies at the intersection of 1 and 10, UT and TSR. Its old value is 4. Its new value is 1 plus 10, which is 11. We select the smaller of the new and old values for Q3. So we select 4. And the old path is left as it is. Concentrate on the US entry. It lies at the intersection of 1 and 3, UT and TS. Its old value is 9. Its new value is 1 plus 3, which is 4. We select the smaller of the new and old values for Q3. That is, we select 4. The resulting path is found by concatenating UT and TS, dropping one of the repeating T's. So the path is UTS. The last entry in Q3 is UU. See that the old value was 11. The intersection values are 1 and 5, which will give us 6. Since 6 is smaller, we opt for it. Now what about the resulting path? 1 is UT, 5 is TSU. The resulting path should start with U and end at U. The T is repeating, so we drop one T and the resulting path is UTSU. This completes our matrix for Q3. Keep Q3 in front of you. Now we are going to start another iteration in which we will work out Q4. This will be our final matrix. Fix the fourth row and the fourth column to compute Q4. This is what I want you to do. I have taken away all the other elements and I have highlighted the fourth row and the fourth column. Intersection values will now be sought from this row and this column. Let us walk through each element. First focus on RR. The intersection values are 4 and 7, which will give 11. The previous value was 7. So we keep the smaller but older value, 7. Come to RS. The intersection values are 4 and 7, which will give 11. The old value was 5, so we opted for 5. Come to RT. The intersection values are 1 and 7, which will give 8. The old value was infinity. 8 is better. We commit 8 for RT. What about the path? 7 is our SU, 1 is UT. U is repeating, so the path that we commit for 8 is RSUT. It begins with the row, ends at the column. This completes our row for R. Now I will talk about the row for S. Look at SR. The old value is 7. Intersection values are 4 and 2, which will give 6. So we opt for 6. 2 is SU, 4 is UR. The concatenated path will be SUR. Look at the entry for SS. The old value is 12. Intersection values are 2 and 4, which will give 6. We commit 6. 2 is SU, 4 is UTS. So the path is SUTS. Look at the entry ST. The old value is infinity. The intersection values are 1 and 2, which will give 3. So we commit 3. 2 is SU, 1 is UT. So the resulting path is SUT. And this completes the row of S in Q4. The last row to fill is the row of T. Look at TR. The old value is 10. Intersection values are 4 and 5, which will give 9. So we commit 9. And what about the relevant path? 5 is TSU, 4 is UR. The path becomes TSUR. Look at the TS entry. The old value is 3. Intersection values are 4 and 5, which will give 9. So we opt for the old value and the old path. Look at the TT entry. Intersection values are 5 and 1, which will give 6. The old value is infinity. We opt for 6. What about the resulting path? 5 is TSU, 1 is UT. The resulting path becomes TSUT. And finally, Q4 is complete. This matrix shows the shortest paths between all node pairs in our graph. Analysis of SPA. There are n iterations in SPA. SPA computes an n by n matrix in each iteration where n is the number of nodes. So the time is O(n) cube because you work with n squared elements in one iteration and there are n iterations. In each iteration, it uses 2 times the space taken by a matrix of n by n. Why 2 times? Because we keep an n by n matrix for the weights and another n by n matrix for the paths. So the space taken by the shortest path algorithm is O(n) squared. The shortest path algorithm is one of the most important algorithms in communications. Your homework is to consider the weighted graph shown here. For the weighted digraph, find the weight matrix. Then execute the shortest path algorithm for the same digraph. From the weight matrix, derive Q0 and then iterate as many times as necessary to get a matrix which gives you the shortest paths between all pairs of nodes. What did we learn today? We found the weight matrix for a weighted digraph. We executed the SPA on a weighted digraph. And we investigated the time and space complexities of the SPA. I want you to read the book, do the homework that I've set you, note your questions, and email me your suggestions. Take care. Allah Hafiz.